Hi, I'm Ken. I started this channel to get a conversation going between regular people like you and I that are just really interested and fascinated by quantum physics and experts who can hopefully help explain it. Since entanglement seems to be a really hard topic to both explain and understand, I thought I would start with that topic. So if you're anything like me, you love anything quantum. It's very fascinating, intriguing, and whatever. But even if you watch like 1,000 videos, you're just left unsatisfied. It's like there's got to be more to it, and you can kind of feel deep down inside that you can understand it if it was just maybe explained a little bit different. And if you're like me, you get tired of hearing that quantum is weird or mysterious or there's a cat in a box and it's both live or dead. That stuff is just not very helpful. So enough with the rant. I decided to do something about it, and I built the device that you're looking at, this Desktop Entangler, because I wanted to like touch and feel the particles and just see what's going on as they're being entangled. And so in this video, we're going to entangle some photons. So first we're going to take a step back and look at what the lab equipment would be and then how it compares to the Desktop Entangler. Now you've probably seen some videos with some very expensive looking equipment. You got lasers and lenses and electronics and all that all over the place. I think this diagram does a good job of just explaining like what the basic parts are. And it's my understanding that there's some kind of photon source, a fancy light bulb or laser, because that's what photons are. Light creates photons, or light is photons. And those photons go through a crystal called an SPDC crystal, which stands for spontaneous parametric down conversion. I'm just going to call it crystal from this point forward. That's too long of a name. Anyway, inside the crystal, that's where the entanglement happens. And what that crystal does is it splits a photon in half, and the two smaller photons, one goes to Alice's filter, one goes to Bob's filter, and they report back whether they passed through the filter or were absorbed. Now, it's not really a half a photon. There's no such thing as a half a photon. It's a photon with half the amount of energy, but it's a good visual to think of a big photon kind of breaking into two smaller ones and going out to Alice and Bob. And so we're gonna just stick with that. Now, one other thing to note here is that there are other types of entanglement besides Alice and Bob seeing the opposite outcomes. They could see the same outcomes, or they could see a mix of pass and absorb that sort of follow a pattern, and it's a cosine pattern. We can talk a little about that later. So in this experiment today that we're going to do, we're just going to look at the case where Alice and Bob see opposite outcomes because that's the most common experiment that's talked about. So the Desktop Entangler kind of works the same as the lab, except you got to take it and turn it 90 degrees so that the photon is coming from the top and coming down to the entangler, being cut in half, and then going out to Alice and Bob so that they can measure them on their filters. Right. So take a little closer look at the components here. This is a photon, classically speaking. And what we're going to see later is that when we measure at some angle, there's going to be a pointer, and the pointer is going to stop at white if it means the photon passed through a filter. It's going to stop at black if it is absorbed by the filter. And then the other feature that you can see here is there's this curve that separates the white and the black. And that is actually exactly a cosine squared curve. And if you've heard of Malice's law, the amount of photons that go through changes with the cosine squared of the angle. We're not going to get into that right now, but that's why that curve is there. Now, The photons can be configured in the entangler in different ways, and this creates different entanglement patterns when we pair them together. They can both have white tops, they can both have black tops, it can be one of each, or the whole photon itself can be rotated around out of phase. So if we were making what's called a correlated pair of photons, we would entangle them so that they look like this, that they're exactly the same, and then Alice and Bob would get the same outcomes. If we configured them so they're anti-correlated, it's called, then Alice and Bob would always get the opposite outcomes. And we're going to step through how that looks here shortly. Now the other part of the entangler is these two detectors, and they're shown side by side, but they're separate. We could actually ship one of these out to Alice and one out to Bob to kind of demonstrate that even at a distance, these photons will appear entangled. The shaft that the photon rides on is the direction of motion, which again is from the top down to the bottom. The pointer is shown in the picture there, and that points to white or black. The gray sort of gadget there is the filter, and you can see a dial along the bottom, and those are degrees, so we'll be able to set the filter at a different angle. And then finally there's a height adjustment, so you can actually move the photon up and down in the detector, and we're gonna show that that actually makes a difference on the outcome of the experiment. So the very first experiment here, we have Alice and Bob. They've decided they're both going to measure at 60 degrees, and we're going to walk through everything step by step. We're going to prepare those photons in the anti-correlated state. We're going to assign one of the detectors to Bob and another one to Alice. They're going to go off. They're going to measure at 60 degrees, and then we're going to check. Do Alice and Bob have opposite outcomes, meaning one of them has white, one of them has black, or in other words, it passed through the filter or it was absorbed through the filter. So we're going to kind of go step by step here, very slowly, frame by frame. We have a large photon coming in from the top, and it's heading down towards something that looks like a blade, because remember, part of what the crystal does is it cuts the photon in half. So let's go ahead and do that. It's going to drop down, and there. It's broken in half. Again, figuratively speaking, but we're going to stick with that analogy. It's two smaller photons, and they're going to make their way over to the shaft. And remember, the shaft is the direction of motion of the photon, and it's going to snap into alignment. And you can sort of think of like two magnets when they snap together into alignment. We're suggesting that's what happens to the photons inside of the crystal. And then they're going to drop down deeper and deeper into the crystal or the entangler here. And at this point, we're just going to remove the vertical blade that was sitting there just so that you can see. And then we're going to rotate the camera so that you can see a little bit better. And then we're going to remove the we're going to move the photons so that they're aligned in that anti-correlated state. And I'm going to click through here, and right now they're still out of alignment. They're a little bit more aligned, getting more aligned, and okay. Now they are completely entangled. They were split in half, they were separated, and now you can see that one has a white face, one has a black face, and the tops of them are also opposite. So these are anti-correlated. They're in a very specific kind of alignment. And by the way, it wouldn't matter if you switched these around. You could put the one with the black top on the left and the white one on the right, and then later you would see that Alice and Bob just get different outcomes, even though they're still opposite. But let's just keep going here. So now Alice and Bob have agreed to measure at 60 degrees, and you can see the red entangler has been removed and the filters have been put back on. and they're both right lined up with 0 degrees if you kind of look on the left hand side there. And I'm going to start moving the filters toward 60 degrees, and we can talk through what happens there. So here's Bob and Alice's filters at 10 degrees. Here's 20. Now we're at 30 degrees. And just take a look here. Alice's is pointing to white, and Bob's is pointing to black. So they're opposite. But if I click one more, now they switch. Now Alice's is on black and Bob's on white, but they're still opposite. So we're changing angle, but we're maintaining the oppositeness of the entangled particles. Well, let's move to 50 degrees and then to 60. Okay, we're at 60 degrees, and you can see where we ended up. Alice's outcome is black, or her photon was absorbed. Bob's outcome is white, and his passed. And if you think back, if we would have skipped the entanglement process, what would the outcomes be right now? Well, they'd be random. Who knows? Alice could have black, Bob could also have black. They might have white. Any combination would be random. But we entangled them. We aligned those photons in a very specific way so that when we rotated the filters around, it would maintain opposite outcomes. So now we're going to run the experiment again, only this time we're going to change the height, because we said, hey, something happens if you change the height of the photon. So let's take a look at that. So again, we're going to measure it. We have Alice and Bob measure at 60 degrees. That's the same. We're going to re-randomize the height. The height in the first experiment was already randomized. We're going to re-randomize that, and we're going to kind of jump ahead past the entanglement steps since you've already seen all of that. And we're going to go right to assigning a detector to Alice and Bob and see what happens when they measure at 60 and find out at the end, do they have opposite outcomes or not. So we're jumping in here, and this is what it looked like previously. And I'm gonna toggle back and forth. In the previous experiment, the photons were higher on the shaft. Now they're lower, and I'm gonna go ahead and start measuring here. Now we're at 10 degrees. We're at 20 degrees. We're at 30 degrees. Now notice a difference here. Alice's pointer is nowhere near changing from white to black like it was before. The last time when I clicked one more step, it went into black, but now it's staying on white. Here's 40, here's 50, and here's 60. So Alice's outcome is now white instead of black, but Bob's is opposite. That's what we were trying to prove, that they were opposite. But you can see that they each experienced something different this time. And why is that? How could that be? That's because the height changed, but the alignment, the entanglement didn't. So the patterns are still a reverse image of each other, the white and the black. So it doesn't really matter what angle you measure at. It's always going to be the opposite. And we could run this experiment 1,000 times right here. And Alice and Bob can even measure at different angles. They could measure at 20 or 70 or 90 or whatever. It doesn't matter, because they're entangled, because they're aligned like that in the beginning with the opposite white and black face. That enforces them to have opposite outcomes, even if they switch off who gets the white and the black. So that's it. What you just saw was the famous Alice and Bob entanglement experiment, where they observe opposite outcomes. I hope that you found the Desktop Entangler helpful to kind of visualize and walk through. I would love some healthy discussion here in the comments. If you are more of a curious viewer and you just kind of like quantum mechanics and those kind of topics, just post in the comments whether you thought the quantum entangler was useful or not. Also post like what else you want to learn about. What other quantum topics maybe haven't been explained in a way that resonate with you, and I'll try to come up with different kind of desktop models and ways of explaining it. If you are a quantum physicist and you happen to run into this video, it would be great if you could post some feedback. Let us know. Is the quantum entangler doing an okay job illustrating entanglement? And if not, what's the difference between what we just saw and more traditional theory? So again, let's just get some conversation going, and hopefully we can all start to become much more satisfied in our understanding of quantum mechanics. So thank you so much for watching. This is the first official video on the channel, and I hope to see you on the next one. Thank you.